we'll have plenty of time to talk about more. So. We're about to run through everything today. The objective, going back, we have non-ideal conditions, and we got to figure out how are we going to get to the thermodynamics, which is just wonderful. It tells us all we need to know about the universe. How do we get from the thermodynamics to the material through that non-ideality? Well, we decided, because we like equilibrium constants and how they were used for vapor pressures, or whatever the case may be, we'll invent a term called the activity. Yes?
My homework wasn't in the stack.
We got an extra?
Oh, thank you. I'm sorry.
Take it back.
Here's the one I wrote on there, laughing at your copier.
Oh.
She brings them in, she makes copies, I guess, for her own purposes while I have them. And her copier just brings gray streaks down the whole thing, so I kind of laugh at her about that. It's beautiful. Sorry, I just always know it's you when I turn to that one. All right. We have measured what we put together, what we build, laboratory quantities. We have A, which is thermodynamics. It ties to the Gibbs free energy. So the activity coefficient then puts them together. So all it comes down to is we'll need to do two things. Go into the lab and build something. Build a solution of a 0.4 mole fraction. Measure a boiling point. Fan to vapor pressure. Whatever it may be. We make a measurement. We then compute an activity by, so far, one of four ways. We're going to have a fifth one and a sixth one today. If the material is volatile, it produces a vapor pressure. And if it is in high concentration, then Rayle's law is ideal for this. It works very, very well. You get activity coefficients that are nearly 1. If the material is in very low concentration, we're going to use Henry's law, so it's just a designation out of that. Now, if we have a material that is non-volatile, then we have to do some other means. We had come across two of them. One was measuring the freezing point depression and see how that produces. Then we also we can measure the boiling point elevation. So if I put salt water together, measure when it freezes, I can get information about the non-ideality of the salt water. And for the fusion or boiling point the same way. Now, for these two, we had a case where if we had a very, very dilute solution, which is, it's hard to get, but if they're a dilute solution, then we have this, dilute solution approximation where we have that the delta T freezing was the freezing point constant times the molality of the solid, or solute A. And we had another one, you saw these, delta T boiling as the Kb times the molality of the substance A. One qualifier on that. When you were back in little general chemistry and we kind of talked about all this thing, they gave you another factor called the Van 't Hoff factor. The Van 't Hoff factor was put into place by putting a little I within here. And that took the place, if you had, for example, sodium chloride. Well, sodium chloride, when it goes into solution, breaks up into two particles, sodium ion and a chloride ion, so you get double the effect. That's why we pick our salts very carefully when we put them salt out on the road. You want materials that have a lot of ions in it, so that it'll bring the freezing point down even lower. What we know now, because you're smarter now, is that this Van 't Hoff factor is kind of a fudge factor, and we're going to the activity coefficient is really the better way to go. But I just made a little side note of that. I didn't address using this, and I'm not going to worry too much about it. All right, so that's in the four ways we have. And if I also have another way, and to do that, I would reiterate, I don't know if you are familiar with osmotic pressure systems. Just kind of give you a brief background, I do this in Gen Chem, you may have seen it. If I have a solution here, and within this solution I've got actually a membrane. The membrane is porous to the solvent only. Okay, the solvent can go through that membrane. The solute cannot. It's called a semi-permeable membrane. Well, if I have, let's say, a salt water over here, so I have sodium chloride or whatever's in there, and here I have pure water, what's going to happen, these two have different, here I'm bringing back a term that I introduced a little bit earlier, chemical potential. One has a different chemical potential than the other, different potential energy. Well, you know, if you have a difference in potential energy, things tend to fall. If I have a higher gravitational potential, things tend to fall to a lower gravitational potential. Same thing for chemical potential. So what happens in this instance is the water is drawn over to the other side in an attempt to dilute the salt water, all right? And over time, what happens is this system comes down here, the system comes up in here, and it comes to an equilibrium point. Now, the only reason why that it stops, sorry Ferguson, but not good. The only reason it comes to a stop is the same thing we looked at with mercury columns and a barometer, is that this is being pulled down by gravity. So it finally counteracts that effect. And in fact, this height that is achieved is, it produces a pressure because of that, same way we calculated before, and it's called the osmotic pressure. And so what we can do then is we can use that osmotic pressure to get an activity again. On a side note, if I take this up into a gravity-free environment, what do you think would happen? What's that? What would be zero?
All the water would go to that side.
If you're saying gravity free, then that means that J's
That's a good point. I've not thought of it in that way. It wasn't really the question I was asking, but there's a really good answer to it, by the way. Because there's no pressure, there's no gravity. You outsmarted me, damn it. Why put it on the calendar? It ain't gonna happen again. But what would this thing look like if you took it in a gravity-free environment?
All over the other.
There we go. Go all over the other side. There's nothing pulling anything down, which makes her correct again. Damn it. All right. So now, so what we can do then is take a system, put that in place, and come up with another activity expression. And the activity for an osmotic pressure is given again without derivation. You produce kind of an interesting. I write it differently than I have up here. It's E to the minus osmotic pressure, molar volume of B. I'll talk about that in a second. Times, or divided by R times T. I have it up here in form of a logarithm, but I have it in your homework in kind of a different way. So what I do, I would take a saltwater system, I would measure this whole thing. This, by the way, this is the molar volume of the solvent. Okay? So it's the molar volume of the solvent in this instance. So we could get that from the density. For example, have the density of water is 1 gram per milliliter. I flip it upside down, that's milliliters per gram. Then I multiply it by molecular weight, I get milliliters per mole. Milliliters per mole is molar volume. So we can always get that. But this, again, is the activity, and as all of them will be, the activity will be expressed by this. So it's simply a measurement. Now before I go on with this, let me just kind of pull a homework problem out, right, and make a point on this. On the non-ideal solutions, I do a little bit of a write-up on here, and then I put all these expressions together on a page. So I have for volatile components, Rayleig's law and Henry's law, and then for non-volatile components, I have freezing point depression. There's the expression there. Oh, by the way, this is E to the this. I'm sorry. It's correct in the homework. So I had these expressions for the freezing point depression, boiling point elevation, osmotic pressure, and so forth. Okay? And I have a little discussion in there. Now, what that leads us then to the problem. Problem 6, we'll look at the 6 and 7 now. As I give you a solution of 6 grams of glucose, I give it its molecular weight. I'm going to dissolve that 6 grams in 0.140 kilograms of water. Okay? So with the grams of glucose and the molecular weight, you've got moles of glucose. Moles divided by the kilograms of solvent, of course, is a molality. So with the data that I provided for you, you're able to produce then a molality of the glucose. I said, I give you then a freezing point and also a density of the solution. That's to allow things to be taking place. So one, calculate the molarity and the molality of the solution. You should be able to do that in short order. And find the activity of the water in the solution. Well, you can do the, I've given you also some, I give you should be KF. That'd be. I think I need to give you a KF on that. I may put that in place. Well, what we'll do is we'll calculate the activity of the water. And so I'm giving you a freezing point. You should be able to use just the freezing point expression, but again, you need a delta H of fusion. Giving you the freezing point, the pure freezing point of water, of course, is 273.15 Kelvin. Kelvin, please, for all these things. And so I will get you that number, and I'll put it up on the website, or you could look it up, and you want the enthalpy of freezing or delta H of fusion for water. So that'll allow you to calculate the activity of the water. Now, the point that I make in part C is that the activities calculated by this, and this means are all the same. They should be the same number. So once you have this number calculated from this, you can then take that number here and calculate a boiling point. Right? In other words, run that backwards. And by the same token, you're asked to calculate the osmotic pressure. You can do that in the same way. So you're going to use this to solve for A of B. Put that down in here, put it down into here, and then solve for the vaporization. Solve for the boiling point and for the osmotic pressure. Just saying that you can relate them all together. They're not independent of each other. Like I said, I've given you a delta H of vaporization. I will provide for you, before I leave today, a delta H of fusion on the website, and then I'll update this. Unless I have it somewhere else. Didn't you do, you did a calculation, that's benzene though. I was just seeing really quick if I had it somewhere else in the homework. It may have bit the dust when I cut this down a bit. I'll get on the way. Okay, now, I've given you then in part D the ideal expressions, all right, for the delta T boiling and osmotic pressure. So from those expressions, calculate the boiling point and the osmotic pressure of the solution and compare. When we do it right, and we do it by dilute solution approximation, how close do they come? And I've given you the ebullioscopic constant for water of 0.91 degrees centigrade per mole out, okay? And that is simply have you observe the differences between those. So calculate A from this, use it into here, calculate the other quantities, and then use these expressions. And of course the pi is the molarity times R times T. That's the other one that we gave you in general chemistry. And just the same way I derived this, or I have the derivation of this, I didn't actually do it, you can produce it. It's a dilute solution approximation on that. So it's a straightforward problem to do, just kind of going back and forth. But keep in mind that an A calculated from here is the same A here, is the same A here. All right? It's also the same A here. It is not the same one here. Okay? Don't worry about it. We're not going to talk about too much about that. It's getting into the weeds a little bit. In problem 7, I gave you a non-ideal vapor pressure diagram. Let me just outline it here. You're going to do this. And this stuff we'd already talked about, but just kind of give you. So let's say I have Okay, so let's say I have something like that. Okay, so I'm just asking you to simply draw in the Rayleigh law line. Now remember Rayleigh's law, which says that the pressure is the mole fraction times the pure, is the one that converges up in here. So you start here, and you draw a straight line. That's the Rayleigh's law line. And same here. You start at 0, you start at here, you draw a straight line back. Now the total pressure, ideal, is then connected those two dots there. So that produced those graphics that I had way earlier, where I had these start up. There's that total pressure there. So you're drawing these lines in, and there's your total pressure. You'll need that for a later exam. Okay, now I want to calculate the activity and the activity coefficient for both components based on a Rayleigh's law standard at different mole fractions of A. Now notice in one case, the mole fraction of A is 0.2, fairly low. Rayleigh's law is not so good. Then I have an X of A at 0.83, which Rayleigh's law is better. Well, to do that, remember, this is calculating the activity through Rayleigh's law. So you'll simply go to the graphic Or let's do I have the data there? Actually, you have the numbers. I've given you the numbers right there, so you didn't have to read it off the graphic. So for example, I have an X sub A of 0.2. Okay? The vapor pressure for A is 272. So P of A is 272. And if you want to calculate this, this needs to be then the pure. Okay? Well, you can get the pure for A by looking again on the table that I provided. When the mole fraction of A is 1, it's pure. And the vapor pressure that it gives is the pure vapor pressure. So your pure vapor pressure for A, so PA pure is 512 in that table. Okay, that'll allow you then to calculate the activity for that material at 0.2. And then you do the same thing at 0.3 or 0.83. And then I ask you to calculate the activity coefficient. Once you have this, this is set equal to the activity coefficient times the mole fraction. I'll be consistent here and use B. So you'll have this calculated. This you know, that's that number there. And you just calculate the coefficient. See which one's closer to 1 based on that standard. And you should be able to do that. And then C, I ask you to draw in the Henry's law line for both components and calculate the Henry's law constant. Well, the Henry's law, remember, is the slope of these lines near 0. So for this component here, the Henry's law line will probably draw something like that. And over here, the Henry's law line is drawn in this way. And that's what I had done in the notes when I built the system. Did something like this. So here's a similar diagram. So there's a Rayleigh law line. It goes from right to 0 in a straight line up to the pure. The Henry's law line, I follow this down. I say, well, that's the slope of that line. I can get a straight edge and draw that up. So the slope of that line is the Henry's law constant for that material. Slope of that line, that blue, but I can barely see, I gotta change that. Slope of that line is the Henry's law constant for that component. So then you'd be able to produce those. And then in D, I want to calculate the ideal solution vapor pressure in an equimolar solution of A and B. So both of them mole fractions of 0.5. And so that's why I had you draw this line here. So this line, when you had the Rayleigh law lines, put them up here, drew that total. So at 0.5, you'll calculate that. So do that on the Rayleigh law line. So for this one, this would be 0.5. I would come up here, and two ways you can do it. You can either just take that number there, add it to that number, or if I draw a line up here, I can just kind of read that right off there. So I want to see what is it if it's ideal, and then you can compare it to what it is non-ideal. And finally asking about positive and negative deviations from ideality and what are causing those. So fairly straightforward on that, but I want to kind of go over that in just a little bit kind of quickly. Is that, did we go too fast? Is that all right? So kind of outlined how to do that. Okay. All right. All right, so that gives you, we have ways to get to the solutions in doing this. Now, however, there is a minor problem, and there's a minor problem with these that I had and the ones that are doing in there. The activities that you're determining are, for example, in a salt water or the sucrose solution or glucose solution, the activities you're measuring by the boiling point and freezing point are the activities of water. Or, excuse me, let me correct myself, of the solvent. You're measuring activities of the solvent. Well, the question is, the reason why is that the measurement that you're making has the properties of the solvent. When does it boil is when the solvent is boiling, not when the salt is boiling. When it's freezing is when the solvent is freezing. So we have to figure out, okay, how can I go from the solvent and figure that out and then get to the solute, which often I'm more interested in. Well, there's two ways to go about it. One's fairly straightforward, but one is very difficult, and I will just simply show it to you, and I'll look for anything that gets woozy and falls over. But we won't do it, but it's just by description. Now, one way to get to the activity of the solute is by, particularly if you have ionic materials, is by the electrostatic attractions. You have positive, negative ions, and electrodynamics is very, very good at figuring out what charges do when they're involved next to each other. Well, in a fairly lengthy and extended derivation, there is a way to produce an activity coefficient from all of this information. And that activity coefficient is through a set of ionic solutions. Now let me describe what's happening, for example, in here. We have a problem a little bit in that I can't measure the activity of sodium ion independent of the activity of chloride ion. They're always together. You always have a positive and negative ion. So here's what we do. If I have, let's say, sodium chloride, and I say, what is the activity of sodium chloride? What I'm going to do is express it as in kind of an average. So this is going to be a activity, what is called the mean ionic. This is just definition. In practice, it will be fairly easy to do. The way I will write it as this, I will write it as the molarity of this sodium ion multiplied by the molarity of the chloride ion multiplied by the activity coefficient squared, where this is called the mean ionic activity coefficient. So I can't find gamma for sodium ion and chloride ion. I just have to find just the average. That I can do. So when we do equilibrium, we're going to do one in just a minute. The equilibrium concentrations of stuff, the activity of the salt will be the concentrations times this average squared. That's how we're going to have to go about it. And I kind of do a little example here. If I've got the activity, what's the activity of 0.15 mole or molar sodium sulfate? Well, for sodium sulfate, I do it in the same way. Let's do another one here. So for Na2SO4, the activity will be the molarity of the sodium ion squared times the molarity of the sulfate ion times the activity coefficient, now cubed. You add those numbers together. Okay? So unfortunately we have to do that, but that's the way it's the case. So I had a 0.5 one here, so I take the 0.5 squared and I get the 0.0338. Okay. Now once we have that, we understand kind of what that is, kind of figure out, can we calculate it? And if I have ionic solutions, it turns out that we can. You may have seen this. How many of you had quant? Most of you have. Did you talk about Debye-Huckel? You should in quant. You really should. I have to talk to somebody about that. There's something you should see in quant because it deals with solution. You're going to see why in just a moment. But there's a way to calculate it called the Debye-Huckel. And it's got an umlaut over that, so when you say it's supposed to be Debye-Huckel. There. We got the Debye-Huckel theory, which is expressed as a logarithm. It says that the log of the activity coefficient, and that's this mean ionic activity coefficient, is equal to minus a constant, called the Debye-Huckel constant, and then you have, this is the charge on the cation, the charge on the anion, absolute value. So for sodium chloride, this would be 1 times 1. For sodium sulfate, this would be 1 times 2. Okay, you just put the ions in there. Then you multiply by this curious little quantity. It's a square root of I. Talk about that in just a minute. Divided by 1 plus the square root of I. Now, I is called the ionic strength. And it really, really, really plays a major role in how things happen. We just did an experiment yesterday where I tried to dissolve to make a saturated solution of something. Well, we did a saturated solution in water and a saturated solution in an unrelated salt, and big, big differences because of these effects. We're going to see how they come about. You'll see an example of that very soon. Now, the ionic strength is easily calculated, and there's obviously an expression for that. It's given down in here. It says that the ionic strength will be 1/2 times a sum of, you're going to have the concentrations of, let me put it this way, the charge on the ion squared times the concentration of that ion. And I have a couple of examples to show how this works. Let me do one, for example, for this. Which one do I have here? Okay. 0.5, 0.5, 96. Okay. This value, gamma, is 0.05926. Did I get that right? Oh, 0.50926. A little bit of dyslexia going on there. 0.50926. It's just a constant. It comes about by a number of different means. All right, so if I wanted to calculate an activity coefficient or something for a solution, I do this, and I do it in a couple of different ways. So let's say that I have 0.035 mole solutions of HCl, calcium chloride, and zinc sulfate. So let's do that. So we have a molality equal to 0.035. Okay? And I want to do HCl, let's say it was zinc, or calcium chloride, excuse me, and zinc sulfate. Okay? So I want to do that and calculate the activity coefficients. Well, first, to do this, this is my target here. To do this, I need to get those. So I want to do those. Now, for the HCl, I'm going to follow this. It goes like this. So I for the HCl is 1/2. And now I say, well, I've got hydrogen that has a charge of 1. So it's going to be 1 squared times the concentration 0.035. That's the hydrogen. And I do the same thing for the chloride. That's plus then. The chloride has a charge of 1 as well. It's 1 squared. -1 and -1 squared becomes 1. Then times its concentration, 0.035. And in this instance, you get as an answer 0.035. Okay? Let's see how things change when I do these. For the calcium chloride, this is 1/2. Now, calcium carries a 2 charge, so it will be 2 squared, and the concentration of calcium is 0.035. Okay? Then I turn to the chlorides. Be careful here. Chloride has a charge of 1, so it's 1 squared, but I get 2 dozo, Mexican lingo there, chlorides for every 0.035. So that has a concentration of 0.070. Twice. So when you compute that out, you get 0.105. Okay? And then finally for the zinc sulfate, I'll just go over here now. It's 1/2. Now the zinc is a 2 charge, so it's 2 squared. Its concentration is 0.035. Sulfate is 2 squared, 0.035. It produces an ionic strength of 0.140. Well, at that point, it's just a matter of plugging it into the equation for the Debye-Huckel theory. And you see that I have 10 to the power of it. I have logarithm on the board. So I take 10 to the power. There's the constant. For HCl, it's 1 times 1, hydrogen and chlorine. The square root of I that I just calculated, 1 plus the square, I get a 0.831 as an activity coefficient, already showing non-ideality. Now, these are all the same concentration. They're all 0.035, and look what happens to the activity coefficient for calcium chloride and zinc sulfate. For calcium chloride, now it's 2 times 1 up here, calcium 2 charge. For the ionic strength we calculated, we get 0.563, and for zinc sulfate, it goes 0.279. So it gets away from ideality very, very quickly. A point of note is that, and I won't do this, but you know that there are 2 different logarithms. There's a base 10, well, there's actually all sorts of different logarithms. The 2 most common ones are base 10 logarithms and base E, natural logarithm, the LM and LOG. If you use a base 10 or a base E, you have to adjust the constant. So for the constant, in base 10 is 0.51926 that I've just used. I had this one up earlier, but if you use a natural logarithm, it's 1.1726. Just be aware that if you're going to use a particular logarithm, you have to pick the right constant. There's just a little thing that you can take care of. Okay, now, all that's very well and good. How are we going to use this? Let's see how. And this encompasses the last question in the homework. Again, we will come back and look over and practice them, and I'll throw out some questions, and we'll do all sorts of review. We have plenty of time. But what I want to do is I want to calculate the solubility of barium fluoride. So I want this. Barium fluoride solid in equilibrium with barium ions, aqueous, and 2 fluoride ions, aqueous. It has a KSP given of 1.7 times 10 to the minus 6th. Okay? All right, so I'm going to take you back to your general chemistry and do equilibrium solubility problems. When you had done this way back when you were little, you took the solid, you put it in solution, you let it come to equilibrium, and then you drew an ice diagram to begin with. So in an ice diagram, you said, well, I'll produce X amount of this, I'll produce 2X amount of this, and then you put it in the constant. Well, now things have changed just a little bit, and we're going to write the equilibrium constant expression in terms of now activities. So let me write my K now. Instead of writing the molarity of barium times the molarity of fluoride squared, I'm going to write this as the activity of barium times the activity of fluoride squared. Okay? That's how we begin. Now I'm going to replace those activities with concentrations and activity coefficients. So this would be now the molarity of barium, or molality, the molality of fluoride squared multiplied by the activity coefficient cubed. Okay? So that's the way we just take them all, we combine that activity coefficient together. All right, if I now go to this and do now what you did in general chemistry, you're going to do everything the same, except you just got a little tag along here. So you're going to say, well, this is time x. You're going to say 2x squared, and of course the activity coefficient cubed. So you find that the k, then if I take 2x squared, that's 4x squared, times another x is 4x cubed times gamma cubed. And again, when you were little, you said they would ask you to solve for x. You did a little bit of algebra, you calculated a number, we gave you a caramel and patted you on the head. All right, to do that though, let me solve for x. X in this instance would be the KSP, then divided by 4, and divided by gamma cubed. Now all of that to the 1/3 power. Now, of course, when you were in the Gen Chem, we didn't have gammas, you didn't know what they were. So this wasn't here, so you took the 1.7 times 10 to the minus 6, you divided it by 4, you take the 3rd root of it, and you got your answer. Very simple. But now we need to use the activity coefficient. Well, to compute the activity coefficient, I need to do the, what I'm done here. Come here. Pay attention. Be good. Heel, heel. Come down a little. Here. To compute the gamma here, I need the activity or the constant. Well, I got that. I need the charges on the cation. I got that. And I need one, but I also need the ionic strength. Well, I need the concentrations of the ions to calculate the ionic strength. So like we had seen before, I need to know the answer before I can find the answer. All right? Again, there's a common problem. So here's when we solve it. So what I will do is I will solve this problem ideally. So I'm going to presume we'll start and let gamma be equal to 1. That's ideal. I can then produce a molality or a molarity. I'll take that molarity, then from that, calculate an ionic strength. So I'll first set gamma equal to 1 find M, then find I, find a new gamma, and cycle the ring all over again. And I've got that outlined here. So here's what we have been producing so far. I got the molality, there's the K, there's my standard molality. I was a little lazy in doing this up here, but if we want to do this correctly, this should be molality divided by the standard molality, which is 1, just like 1 bar, 1 molal. And this is M over the standard molality squared as well. Let's make sure that it becomes unitless. I just left that off. Okay, so here's what we will do. I will take the same approach. I will solve the system ideally. Using the ideal molalities, I'll calculate a new ionic strength and coefficient. I'll put those values to calculate a corrected molality, and I will repeat that until it converges. So let's see what the number is. Now, on the first path through, there's no gamma here. I have this solved out, and I get a value of 7.5 times 10 to the minus third mole per kilogram. Molality. And of course, that's the ideal answer. Now, what I'm going to do is I'm going to take that answer and calculate an ionic strength. So I take this number, put it in. Now, of course, we're talking about, barium fluoride. So barium has a 2 charge, 2 squared times that concentration. Fluoride is a 1 charge, 1 squared, and there's twice that number of them. So I get a value now of I, 0.022555 moles per kilogram. Take that I, put it into the gamma, calculate a gamma. And when I do that, I get a gamma. We started with 1, now it's 0.736. Okay? Do it again. Take the 0.736. Now, I would take that 0.736 and put it into here and do it. That's exactly what I do. I have the K, I take the 0.736, the computer does it for me. I put it into here and calculate that out. I get now molality 0.0102. Very different. So I now take that 0.0102, calculate another I, now it changes, calculate another gamma, now it becomes 0.705. So it's changing, went from 1 to 0.736, but 0.705 is starting to converge, trying to come up to the same number. So now I'll do it again, calculate a new molality, there's my gamma again, a new ionic strength, a new gamma, and now it's 0.701, and I do it one more time, and it comes back down. So now I'm getting it converged. If I do this one more time, I get the same answer. It comes down. So now there is my ideal result. This is my new result, 0.0107, and the percent error from doing it from ideal is about 30%, 31%. That's huge. And so the solubility being calculated by ideal means is way off, 30% off. And as the ionic strength gets stronger and stronger and stronger, it gets worse and worse and worse. Now, I have to reiterate, say it again and be repeated and be redundant, that this is absolutely requiring that the dibihecal theory depends on being a very fairly dilute solution. As you get into more concentrated solutions, things begin to break down. You have to use better equations, of which they are always developing them. So I just have a little final statement. We'll look at the last homework problem. Say, when does the dibihecal theory fail? And here I've got experimental and computed through the formulas. The activity coefficient now for sodium chloride, experimentally, are these blocks. You see, as the concentrations go up, the calculated begins to deviate. It works out really well, write it down here, fairly close, but then they get off. But what happens if I have something with a higher ionic strength? Well, aluminum sulfate is much higher ionic strength, and you see that one deviates much, much more quickly. So here's my experimental and the calculated. So the ionic strength thing is just a huge, huge deal. So it deviates very, very quickly on that. But it still gives us a means by we can get better results. Now what you are going to do is do a weak acid solution. So I've given you an HClO weak acid. So you're going to do this HClO. This is aqueous in equilibrium with H plus, ClO minus, and this has a Ka provided of 0.011. So a pretty strong acid. Okay? Well, we're going to go through the same procedure. Let me get you started on this. if we have this, we'll write the K, let's write the expression. The expression will be the activity of the hydrogen ion, the activity of the hypochlorite ion, divided by the activity of the HClO. Now, to make the problem a little easier, a little more tractable, I'm going to assume that the HClO is behaving in an ideal fashion. So I'm going to have a gamma equal to 1. So if I then replace this, this will be then the molarity of H plus, the molarity of ClO minus over the molarity of HClO, just like you've done in Gem Chem. But now this I'm going to have gamma of 1, so this will be multiplied by gamma squared. Okay? So of course, if you solve that system, now we're going to begin with, I give you a concentration of 0.5 molarity. So this is 0.50, so it'll be minus x, x, x. You put that into place, so you end up with x squared, gamma squared over 1, or 0.5 minus x. Okay? And again, if you knew what gamma was, you would solve that using a quadratic equation and you would be done. But you're going to take the same procedure, same attack. You're going to go through this, and you're going to set gamma equal to 1, and solve for x, calculate the pH. But you recall, pH is defined correctly as the negative base 10 log of the activity of the hydrogen ion. That's pH. We lied to you back then. Okay. All right? So solve that for x, right? Calculate an activity, calculate the pH. That will be your ideal pH. That's what you do when you're in Gen Chem. Now, having then the values for the concentrations, go back and calculate an ionic strength and an activity coefficient. Keep in mind that we don't have to worry about HClO because it is not an ion. It's only the ions that play a role here. So you'll be able to calculate an ionic strength, an activity coefficient, solve this again. So what I would do is I would solve this in general. I just put it in the quadratic formula, solve it as a function of the concentration, 0.5, and gamma, and K. You'll be able to do that. That way you can just plug the numbers in and they'll pop right out. It works very well if you want to do it in Excel. So anyway, you will then calculate a new gamma, calculate an activity of hydrogen ion, go back until it converges, compare the ideal pH to the pH done with a little bit more non-ideality included, and you might be surprised at how far off it could be. So that's the last problem you will do in there. So I give you a little lead in to test that sort of thing. So anyway, we're done. So now we'll come back, we'll run through problems, I'll throw concepts out. We have a couple of days before your exam pops up. So we'll be throwing through ideas. And then last time I did it, the feedback was kind of iffy, and I hope we get a little better result this time. So I'm going to poke you, I'm going to prod you, and they feed you caffeine before you come in. There's something to get you rolling on that. But you have homework on Friday, homework on Monday, exam on Wednesday.